So I know it's really, really small. I did the best that I could try to do to cram all the information in there. So we've got a lot of stuff stacked in there to try and go through and talk through. Instead of just me walking through it, does anybody have specific questions about any one of these that we would like to discuss kind of in bulk first? Is that a point pointing at the A one? Okay, so what do you want to look at within A?
The pi bond.
Not yet. Oh, so you just want to, okay. Okay, so when we go through and look at A, again, it's really kind of small up there. What you should be addressing is each of the individual pieces as we navigate this. What most students, or at least the first group noticed, actually technically the second group noticed, is that what we want to do is have that kind of red arrow happen. Our leaving group leave. Okay, have the hydroxide come out. The problem with that is hydroxide is a bad leaving group, and because it's a bad leaving group, won't leave on its own. Okay? So that's where what we have to do is activate the OH to act as a good leaving group. The way we go through and do that is we add a strong acid. Strong acid, HBr, we run an acid-base reaction first. That acid-base reaction now turns the OH into water, still connected to our carbon structure, okay, with that positive charge. The oxygen does not want to be positively charged, so it can steal electrons from our carbon structure, and it will then give us our coordination, give us our carbocation, which can then undergo the coordination reaction, or coordination mechanism. I would argue that's drawn fairly well up on the boards, so if you've got it, picture of it, you can take a reference to your notes as opposed to what's written really, really tiny on the screen, but I think I've got it drawn in there. Right? If we're looking through that with the SN1, yes, we're talking about the formation of a carbocation, and that's going to be the largest, most important feature behind this individual reaction. If we go through and look at reaction B, we're going to see a very similar system. We'll note that one thing does change about our starting material. Okay? Instead of showing the starting material with just normal lines, we've added a dash. Why did we add that dash into it? Because most students will go through and only assume SN2 cares about stereochemistry and we ignore SN1. SN1 reactions will still undergo reactions with stereocenters. We just have to be real careful with how we approach and deal with that. We're still going to go through and do the heterolysis. We break the leaving group off. We don't have to do an acid-base reaction because chloride is already a stable leaving group. So there's no activation that we have to run. Okay? So the chloride leaves, we get our carbocation. The bromide can then come in and react. Okay? What wasn't shown in structure reaction A looks like on either the boards or what I've got drawn up is that your nucleophile can come in and attack that carbocation from two sides. Okay? Why? If you look at the hybridization of that carbocation structure, it's sp2 hybridized. There's a leftover p orbital. That leftover p orbital has no electrons in it. That's where the carbocation is sitting or housed. That's where it exists. Okay? All of those terms are poor descriptions of it. We're just saying there's an orbital with no electrons. If we're going to form a bond, the bromide has to supply electrons into that orbital. But the p orbital has a lobe both above and below the plane of the molecule, which means we get two products, two possible attacks. The same thing is happening in A. Right, but if we go through and look at the answer for A, I'm able to go through and just call this one plus an enantiomer. In B, I can't say plus an enantiomer. Why not? Not you, we already talked about it, just so you know. Or maybe we could try it this way, because we talked about it. Maybe you're an expert on it. Why can I say plus an enantiomer for A? Okay, in structure A, there's only one chiral center. With only one chiral center, I'm going to get the wedge and the dash. The relationship between those two products is enantiomers. When we go through and move to B, okay, and we're not going to reference you now, but we leverage your knowledge for A. We look at B. How is B different than A? Again, it's tiny. You can look up at the screen or at the boards. We've got the reaction happening at what we'll call the blue carbon, but we could add that red carbon is also there. What is the issue or special characteristic of that red carbon? It's chiral. We didn't define what its chirality was, okay, whether it was wedged or dashed, but it cannot change through the course of this reaction. So if it was wedged, it stays wedged. If it was dashed, it stays dashed. Why does that become important? When we look at the relationship between those two products, we can't call them enantiomers anymore. The only way we'd be able to call them enantiomers is if the other chiral atom, our red chiral atom, also switched. Since its chemistry is not affected at all by the chemical reaction we just went through, because it's all at position blue, we're not going to get enantiomers, and we're probably better to reference this as diastereomers. Even then, we should be more explicit and try and define what was happening at that red spot. Kind of make sense? Okay. If we go through and take a look at the SN2s, or C and D. So the SN2s are happening quicker. We've got less things drawn because they're happening in a single step as opposed to multiple steps. Okay? Which brings up a statement that we could talk about with the SN1. How many steps are in our SN1? 2, right? How many steps happened in box A? 3. Is the SN1 2 steps? Okay? Sometimes not. It depends on the state of your leaving group. If you've got a great leaving group, then yeah, we can launch straight into the full-on SN1 mechanism. Okay? So when we think about the difference between SN1 and SN2, I would rather you focus on stepwise, more than one step, versus simultaneous one step. Okay? So SN1 isn't 2 steps, it's just more than one. So it could happen in 2, it could happen in 3. Kind of, sort of? So when we move to the SN2, these are all going to happen in a single step. Okay? So if we look at the products for structure C, that one was just shown where we got an inversion in our stereochemistry, which makes sense because we're doing a backside attack. Since our bond was wedged, it makes sense to show the bromine, whoops, I didn't draw the product right, just realized that, as dashed. Kind of, sort of? Okay. If we go through and look at D, D's a little bit different than C. How is D different than C? D's up on the front screen if you want to, or the front board if you wanted to look at that. D versus C. If we look at C, our leaving group was on a wedge. Where's our leaving group in D? It's a straight line. Whenever we have our leaving group on the wedge or the dash, students typically are okay with it. The reason you're okay with it is because when we talk about the chemical reaction, we almost universally place it wedged or dashed because it's easier to visualize what's happening in that process. If we go through and rotate our leaving group so that it is in the plane of the paper, now students tend to have a lot of problems with how we would represent and draw the structure. Okay? Personally, to limit my own confusions within the system, I would never draw the product as shown. I think that is a bad way to represent that structure. I fully understand why people want to draw it that way, but I think it's a bad idea. The leaving group we're showing down and to the right. Where am I showing the nucleophile come in? Down and to the right. That looks an awful lot like the nucleophiles coming in at the exact same location the leaving group is leaving, which is patently false. When we talk about the SN2, it is a backside attack. So what I want to do is emphasize that it's coming in on the backside. If the chlorine is down and to the right, where should my OH be in my product? Up and to the left. There's my up and to the left. To show that chemistry better. What's going to happen with D and H? Well, they're just going to bend away from it, which means the D is still going to be wedged, the hydrogen is still going to be dashed. There's no changes, there's no weird flips of anything. Well, that's not going to change your RNS. It does. It still does inversion, Because look at where your highest priority is located. Down and to the right versus up and to the left. It absolutely still does an inversion. But it doesn't do an exchange of the different atoms around. What do I mean by an exchange of the different atoms? Look at the structure that I don't like. Right? When we look at that structure, what happened to the hydrogen in the deuterium? They've changed locations. No, they didn't. They're actually in the exact same space as the structure that I drew by hand. What happened? We did a bond rotation. We did a bond rotation, and by doing that bond rotation, that's what's causing the hydrogen in the deuterium to apparently change locations. Why? Because we did an inversion, and we're now trying to show that. Right? So why would we choose to draw the thing I've got circled versus my crummy hand drawn? That's ultimately just going to come down to preference. Okay? I genuinely don't think it's anybody trying to trick students. Okay? That we're going to spin it and screw everybody up so they can't figure it out. Okay? Ultimately, really, what I really feel it is it's just a comfort in how we would naturally go through and draw. When we think about the solid lines, they're usually a zigzag left to right. If we look at how I've got mine drawn, my zigzag goes upwards, not left to right. So my preference of drawing is drawing my bonds off the standard axis. If we look at how it's default drawn, we're showing the zigzag on the left-right axis. Okay? So you're looking at effectively a human perception on where those atoms are located, and that human perception tends to be easier in one view, and so drawing easier in one view, so we naturally reflex to drawing structures in that fashion. Okay? Why is that a problem for students? Well, now it looks like all the atoms are moving around. Okay? Except the atoms aren't all moving around, because what did you do in Unit 1? Tested and practiced heavily the different manipulations of bond rotations and how that would change your interpretation of the structures. Why? So that when we draw stuff like this, it's second nature to you. You aren't saying, oh, something flipped. You're saying, oh, you just did a bond rotation. Okay? That was the point in Unit 1, was to make you more comfortable with those manipulations. Okay? When we talk about the relationships between structures, that's also the point, so that when we draw these things out, you realize that those are the same things. Kind of, sort of? Okay. The next big thing, I'm going to delete everything on the slide. Is that okay? Or on the projector? Wait. The next big part of this question, technically, come on, finger. Okay. We could go through and do it for the E1 and the E2. Stop double-clicking. Okay, we spent a lot of time with the SN1 and the SN2. I think you guys did a good job, and I think hopefully you're coming out better with recognizing those things. But this last part here is now go back to those reactions, and for each mechanistic pairing, compare and contrast. You mean find the sameness, for the lack of better words, or differences? Yeah. Because when you go through and look at a reaction, you have to be able to decide, should that be an SN1, or is that SN1, or is that SN2? And you're looking at different parts of an overall reaction to make that decision. So one of the first decisions that you could go through and do is that if we look at the SN1s, what do we notice is happening? What was the sameness for our SN1s? Okay, two products. Multiple steps. In making those multiple steps, what else did you notice? Arguably the most important thing you should remember when it comes to SN1. You've got a carbocation. Okay? So by looking at multiple different types of SN1s, what you're trying to do is find those patterns. What do I notice is similar? What is different? Okay? You might say, well, they had different leaving groups. Did the leaving group change whether you did an SN1 versus an SN2? No, we had a leaving group where it was OH and a leaving group where it was CL. It was still an SN1. So changing the identity of the leaving group didn't really matter. Making sure it was a good leaving group did matter. Okay? If we looked at our SN2s, what did we notice for our leaving groups? I would argue they're the same. That was kind of a dumb choice on my end. Okay, they were both chlorides. Okay, does that kind of make sense? You're starting to see what we're trying to pick out? With our SN2, we had one product. Okay, we had single step. I know my handwriting's bad, but I'm trying to get through this faster. Carbocation, what do we have instead of carbocation? We had a backside attack. What we're trying to do is find, man, I just butchered that all to hell. Find and identify those things that are characteristics. Okay? But those characteristics really stood out at you when you had the whole mechanism in front of you. The big piece that comes in within this unit is you don't get everything. You'll be given the reactants. So you've got to be able to look at the reactants and say, that's going to do SN2. That's going to do SN1. But why? Okay? That why becomes the hard part. Okay? And that's going to come down to what are the components that make up a substitution. Well, in a substitution you have a leaving group, you have a substrate, you have a nucleophile, you have a solvent. So you want to be able to look at those four characteristics. So look at a bunch of SN1s and say, when I look at all those SN1s, what do I notice is true for the substrate? What do I notice is true for the leaving group? You won't find anything for the leaving group. It sucks. What do I notice is true for the nucleophile? What do I notice is true for the solvent? That's what you're trying to pick at. Okay? And in those picks, what you're going to find is that when you look at the substrate, what do we find to be true? Tertiary reacts faster than secondary, faster than primary. Why?
Because tertiary is more stable, or I guess it's bad.
Tertiary being more stable, actually, that puts a lot of electrons in one space. Isn't that really unstable? You're right, but you're only half right. What's more stable about having a tertiary? Why? But more electrons in one space is bad. Someone mumbled it. Carbocation. In an SN1, I'm a carbocation. Which means, what do I want near it? As many freaking electrons as I can. That's why tertiary reacts faster. Okay? So I could look at the substrate. I could look at the nucleophile. And when we go through and look at SN1 reactions for nucleophiles, we ultimately find, generally speaking, they're weak. They weren't that big a deal. Okay? Why not? This is addressed in the lab. Why is the nucleophile weak? Why is it irrelevant to a SN1 reaction? What's the most important thing in an SN1? Formation of the carbocation. Do you have a nucleophile in the formation of a carbocation? No. So if all I care about is carbocations, the nucleophile, who cares? It's irrelevant. Right? So we end up ignoring, for the most part, the nucleophile. We kind of mostly ignored the, what did I say? Leaving group, thank you. Okay? But that could then take us back to the solvent. What will we notice when we look at a bunch of SN1 reactions for solvent? We'll find the solvent tends to be protic. Why? Because the protic solvent stabilizes the carbocation. Okay? So what we're trying to do within this activity is getting you, number one, to start recognizing the patterns, build out those chemical reactions, but then start to look through and nuance the characteristics of those. Okay? That can be very challenging to go through and do because that requires an exposure to a large amount of different reactions, yes? Okay. So with that in mind, where I want to jump, not into 152, that was the wrong direction. Where I want to direct your attention is to the lecture slides, and you may or may not have gotten there. But if we go all the way to the end of the lecture slides, what you will encounter, what is this, the last 10 slides? We've got a general form for our SN1, what we're doing. That's the mechanism. That's what you guys all just drew up on the boards with very specific details. Okay? SN summary, what do I want? Substrate, stable carbocation. Leaving group, it exists. Okay? Nucleophile, weak or irrelevant. Solvent, protic. Okay? What are other things that we observed? Did you observe any stereochemical issues? You had formation of products, 2 products when you looked at the SN1. Complications? Right? Unfortunately, Andrew, we didn't get to it. Remind me, we'll get to it Thursday? Or Tuesday, right? We'll get to that complication on Thursday for the SN1. Okay? But then you've got the SN2, you've got all that. That's lots of different moving pieces that you should be able to figure out. But what you're trying to do is say, what are those patterns? What's good behind those? We then want a logical system to deal with SN1 versus SN2. So let's put it on one slide so all the information is there. But then we got to do it for E1 and E2, and then we got to put it all on one slide so we get the E1 and the E2. And then we go, oh my God, that's still lots of information. Can I put it on one slide? Sort of. And we get one slide. I want to look at the nucleophile. Is it strong? What does that favor? If I have a strong nucleophile, that means I want the SN2. Okay? I have a substrate that's primary. That favors SN2. I have an aprotic solvent. That favors SN2. Right? Heat, yeah, sure, there's heat. Heat typically favors elimination. What would I now go through and do? Well, I have 3 checkboxes for SN2. I have 1 for E1, 1 for E2, and I have nothing for SN1. Just by looking at the components of my chemical reaction, I can now go through and say, I think this is going to go an SN2 mechanism. But I have to be able to narrowly kind of check mark off each of those relative importances. And you may find that you get ties. What happens if you get to the end and you've got 3 check marks, random check marks, don't trust me, 3 check marks for SN1 and SN2? What does that mean? They all happen. And if we looked at the products, that becomes really challenging because how could I nuance SN1 away from SN2 if they both happened at the same time? Probably wouldn't be able to because SN1 is going to produce the exact same products as SN2 and another. Okay? And I apologize to Jenna because she's trying to leave, so I'm going to stop.